Hi, class, and welcome to Chapter 10 on energy consumption. Another very interesting chapter. Please be sure to read these in your textbook and let me know if you have any questions about them. So using energy sustainably, energy is mainly used for transportation, industry, and buildings. And there are buildings that use zero energy, like the Omega Center in New York, 5 years with a zero net energy use. And it has LEED certification and the US Green Building Council, which often there's higher upfront costs to get your buildings completely green, but then they will give you zero net energy use. Energy consumption and policies. So no energy sources are truly clean. Unfortunately, all human activities require energy, from heat and cooling buildings to illuminating buildings and streets, planting, harvesting, and shipping food. 100 years ago, energy sources were local, like wood, basically burning wood, peat, and dung. And now they're worldwide, like fossil fuels, nuclear energy, and electricity. Advantages of the energy source is how concentrated it is, the versatility, the safety, and then the availability of that energy source. Disadvantages of an energy source, we always look at the hazard potential, the environmental damage, and the cost. Energy consumption varies worldwide, and it differs between developing and developed nation, and less than 20% of the world's population uses 60% of the world's energy sources, like us and Canada, as you can see there. Energy consumption use, we can see this shown here. We have fossil fuels, domestic production, supply. So we see the supply and then how it gets kind of broken off into coal, natural gas, petroleum, you see the total supply, the consumption, and then what everything is used for. So this arrow going in are all the natural resources, coal, natural gas, oil. We see the domestic production, imports, the supply, and then we see how everything is used in fossil fuels, consumption, residential, commercial, industrial, and transportation. Energy efficiency. This is the amount of available energy in a source that is transformed into useful work. It ranges from 0 to 100%, where natural gas for cooking, about 100% efficient. Incandescent bulbs, fluorescent bulbs, light emitting diodes, pictured here. This is a look at how efficient these energy sources are. Energy intensity. So this energy intensity is the energy use per money of the GDP. So we see energy intensity is most intense in Canada and the United States and China, especially in recent years. Energy efficiency. So this is how efficient we can make our buildings. For example, super insulated buildings use 70 to 90% less energy because they're able to stay cool or stay hot. So fewer or no windows on the north, east, and west, no large furnace, excellent insulation, small south-facing windows, and air-to-air heat exchange with a concrete foundation. The NAECA sets national standards for appliances, and by 2010, which now is a long time ago, the energy use saved was equal to about 51 coal-fired power plants. So we have gotten better over the years. Energy efficiency, you can have super insulated office buildings with south-facing windows, insulating glass, no furnish. There's a new push for zero net energy buildings, which produce as much or more energy than they consume. High-performing buildings will pay for themselves. Energy costs are about 30% of the budget upfront, but then they will pay for themselves over the course of the years. Looking at energy payback time of about 6 years, you can kind of go through here and see how long it takes for that building to pay for itself. The demand site management. So looking at energy efficiency from a power company, the demand side management decreases the demand for electricity, giving cash rewards or incentives to customers who install energy efficient technologies, and energy companies may give away free energy efficient appliances like light bulbs, etc. And this will benefit both the customer and the electric company. Most energy in gasoline is actually wasted. There's energy lost in the combustion of heat, in braking, idling, there's energy lost in friction with the road, and there's energy lost in moving weight of the car that's not actually passengers. So bad driving habits can also waste gas. So that's a voluntary decision that we can work on. Modern vehicle design, the use of Kevlar and plastics to reduce the weight, We can have gasoline electric hybrid engines like the Prius. Regenerative braking will capture lost energy and they can operate at lower temperatures. And there's some new laws that by 2020, all passenger vehicles must have an average fuel efficiency of 35 miles per gallon, and this includes minivans, light trucks, and SUVs. These are different ways to save energy at home. So set the winter thermostat lower or higher in the summer, use compact fluorescent bulbs, close the damper when the fireplace is not in use, do not block vents, unplug televisions, install water-saving faucets, use a microwave rather than a stove, keep coils clean on the refrigerator, clean or replace air filters, set your water heater just slightly cooler, and wash full loads only in the washer and dryer and dishwasher, and wash clothes in cold water. Simple ways that we can all save energy at home. In industry, cogeneration is the production of two useful forms of energy from the same fuel. And this is most effective on a smaller scale. So for example, if the fuel input gives energy to the generator, which gives off electricity, then the heat recovery from exhaust gases or steam can be used to heat the water, additional electricity, heat buildings, or other industrial processes. So kind of use that waste from the generator to do something else. Energy conservation requires a change in behaviors and practice. For example, we can reduce our commute length, use public transportation if possible, bike to work, turn off lights when not in use. That is so important. I could probably turn off those lights right now. I do not need those on. Reduce temperature on the thermostat. Some changes would be difficult. Removing substitutes, allowing product prices to reflect true costs of production, and increasing the price of gasoline to represent the true price. So this is a look at the regular gasoline prices per gallon. And again, these are much lower than what they are now. You can see those differences there. And a comparison of energy input for different kinds of transportation. You can see automobile, rail, carpool, vanpool, and bus is the least energy input per person. The flow of electrons in a wire is what is equal to electricity, and it can be generated from almost any energy source. The energy source spins a turbine. So activated, generated. The turbine then turns a generator, which is a bundle of wires that spin around a magnet or vice versa. And then the spinning of those wires in the generator causes electrons to move in the wire, and that is what causes electricity. So that is what electricity is. The source of electricity can be hundreds of miles away, and environmental impacts are far away from those who use electricity. Hydrogen and fuel cells. Hydrogen gas is comprised of two hydrogen molecules. There's large amounts of available energy with hydrogen. It explodes when combined with oxygen, releasing energy and forming water. The advantages is that there's a very high energy density. It can be produced from any electrical source like electrolysis, which we'll talk about. There are no greenhouse gases and few other pollutants produced, and it can be used volatile. It requires special storage, a little dangerous, and it's relatively inefficient. So electrolysis takes electricity, goes through this electrolysis of water where it splits the hydrogen and oxygen. The hydrogen are compressed for storage and transport, and then are combusted to produce water and energy to provide energy for transportation, heating buildings, and electricity. A hydrogen fuel cell is a device that directly converts chemical energy into electricity. So it does this idea of using those hydrogen. It requires hydrogen from a tank and oxygen from the air, and it's similar to a battery, but the reactants are supplied from an outside source. And then it will eventually provide a flow of electrons, which produce electricity. Hydrogen fuel cell vehicles. Hydrogen is not yet readily available as a fuel source there are less than 100 hydrogen fueling stations in the US as of 2013. I'm not sure what that number is now. Pure electric vehicles, you could have a plug-in hybrid electric vehicle for short range trips, flexible fuel vehicles, but these all still use electricity. Energy storage. Many energy resources are not available when we want them. So for example, solar and wind energy can be intermittent, or too much, large coal and nuclear plants are most efficient with constant energy output. So the solution is to store unused energy, but this is less than 100% efficient, and with each conversion, there's less energy available. We can have superconducting magnetic energy storage, compressed air energy storage, electrochemical energy storage, which is in the case of batteries, pumped hydroelectric storage, thermal energy storage, and kinetic energy storage like the flywheel. So the US energy policy objective 1 is to increase energy efficiency and conservation. This requires many unpopular decisions, for example, decreasing the speed limit to conserve fuel or eliminating government subsidies. And objective 2 is to secure future fossil fuel energy supplies, but there are two oppositions to this: environmental and economic. Objective 3 then is to develop alternative energy sources, but who should pay for this? Gas taxes. And objective 4 is to meet the first 3 objectives without further damage to the environment. So do we tax per oil barrel? All right, thanks guys. We'll see you next time for the next chapter. Take care, everybody.